All right. Okay, after this serious talk about production Rust, let's go to a less production talk. So this is kind of just a hobby project, but I wanted to show you a little bit how to write your own interpreter from scratch, and then, well, let's get to it. So here are the contents. I'm just going to give you a little bit of theoretical background. If you have a computer science degree, maybe you've heard some of this. If you don't, I mean, I'm here to guide you into this. Then I'm going to show you the toy language, like the syntax of this language that we're going to implement, or that I implemented. And then I'm going to give you a code walkthrough of the thing. And then I'll try to do a live coding of a while loop, because as of now, this programming language is not Turing complete, and we're going to fix that. All right, so background, overview. So what are the different steps of a programming language? What's up there? So you have compilers and interpreters, and they are split into multiple processing steps, let's say. For the most part, for compilers for both, the first two are the same. So you have a lexing phase, then you have a parsing phase, and then that's where they diverge. So you have a, for the execution of the program in the end, for compilers, you compile it ahead of time to machine code, or maybe your bytecode, and then you have a virtual machine. And for interpreters, you do it just in time. You can have some intermediate representations. If you ever looked at the Rust compiler, you're going to notice that they have like multiple steps, the high-level representation, intermediate level, and so forth. And well, you do some optimization on them. And finally, you do the code generation. Before we get into everything, here's some theory. So this picture I got from Wikipedia. That's when you know it's going to get good. We have a definition of a grammar. This is like the grammar itself, like from this origin, I think Chomsky was the guy who came up with this notation. It's basically a tuple of non-terminals. I'll get to that, what they are, in a bit. Then an alphabet. So in our programming language, that's the Unicode char set. Some relations. So how are these non-terminals and terminals related? And a starting symbol. So where do we start parsing? And then here to the right, you have like this, I said a picture I stole from Wikipedia. You have like a hierarchy of how complex is a language. So there you have, in the bottom center, you have these regular languages. And regular expressions, excluding all this fancy capture group magic, they're equivalent to this regular language or regular grammar. And they are relevant for our lexing part. And then you have the context-free grammar. That's the only other part that's relevant for syntax parsing. All the rest gets too complex. So we focus on just these two languages, or these two types of languages. And yeah, what does it even mean? What can we do? So for instance, if you have like a regular language, you can't handle something like counting parentheses, right? So I don't know if you ever tried to write a regex that says I want as many opening parentheses as closing parentheses. It's not going to work unless you do like this forbidden, or like what I excluded, this capture group magic that some regex engines support. But a normal plain old regex, you can't do that. With context-free grammars, you can do that. And you do that, okay, so here's like an example of a rule. So you have like a non-terminal, which is this capital A, and then you say that capital A is like a string, a combination of non-terminals and terminals. So I'm getting here super theoretical. I'll show you in the next slide an example of how that looks. Here's an example. The first one is as many opening parentheses as closing parentheses. What this essentially means is like this epsilon there on the right, that's an empty string. So yeah. And there you have this S, which is also the starting symbol. You say, I start, then I need the parentheses, something that's an S, which is either, again, an opening parentheses or an empty string. Then I have a closing parentheses. So you can blow that up, and then you have as many opening parentheses as closing parentheses. Here I have another example, just like to show something. You have with multiple rules and multiple non-terminals. So again, like the capital letters, they are essentially the non-terminals in this language. And then the A is a terminal, so that's an actual letter. And then here you have, for instance, yeah, like you have the start. The start starts either with an A, the A non-terminal, or the B. This A is either an A followed by a non-terminal B, and the non-terminal B is either an empty string or a B followed by an A. So you have alternating A's and B's. I mean, just to show you an example. All right. What can we do with this? First, we're going to do the lexing. Lexing is essentially just the idea of turning text into a stream of tokens. Like I said, it's based on a regular language. Regular language can be expressed as a regex. And actually in the code that I'll show you, that's exactly how it is expressed. And we essentially, all we want to do is just turn this text, this raw text, into like a stream of tokens, because it's really annoying later in the compiler to deal with, yeah, like you have to think, okay, this L, is this the start of a let keyword, or is it the start of an identifier or something? So it's like you want to like get that step out of the way just by doing like a pre-processing pass. All right, this is really easy to do with the logos crate, which I use. It's also the only crate I use in the project. All the rest is written by hand. And that's the lexing phase. So next, after you have done this, you do the parsing phase. And this is where things get a little bit more complicated and where this whole grammar rules and so forth get into effect. You want to turn like this. Okay, let's imagine we have already lexed this text on the right. You want to turn that into an abstract syntax tree. So you want to create like a tree, well, with these rules, to kind of get like some structure into what you're doing. All right, how do we do that? It's not magical that this tree will suddenly appear. There are actually ways, loads of ways to do it. Like you can have like a top-down parsing with a recursive descent parser. You can use parser combinators, which is also something you can do with the nom crate. Then you have bottom-up parsing. Actually, like there are shitloads of ways. But for programming languages, I think pretty much anything I've seen, and I looked at a few implementations, is done with this recursive descent parsers, which is like a handwritten type of parser. And that's what I did as well. All right. Yeah, right. Then there's the final step. So before you think I'm not going to show you what a recursive descent parser looks, I'll show you later. The final step is where this executing stuff, I just wanted to mention here. Because actually I'm not going to do it how real programming languages do. I'm just going to go down the tree and then execute them live, because I mean it's really slow, but it's really easy to implement. All right. Okay, so let's have a look at the rules of my toy language. It's a bit more complex than this example I showed you before, but essentially it's the same thing, right? So we start with a list of statements. So we have here statements. I'm kind of using my own made-up syntax of these rules, but here, okay, you can imagine it's like a bit like a regex. So a statements is a list of statements. What is the statement? A statement is either an assignment, an expression, or an if statement. If statement is an if keyword followed by an expression and then a block. A block and so forth and so forth and so forth. So we're essentially like, I mean, you can already kind of imagine in your head that this is then also these functions that we're going to use. And we're going to essentially follow them like, maybe you can't, but you will see it in the code soon. One thing of note here is like when we get down to the expression part, this is where things get confusing. So I say an expression is a comparison, but I mean, it's not really just a comparison. You can also have a term. So I define it this way, like you have like, okay, I can use the shadow. Okay, so you have here like these two parts, like this term, or you have a term followed by a double equal sign, like the equal sign in any comparison, and then another term. So meaning that either comparison is actually a comparison or it's just a term. Why do I do that in this weird way? essentially it's to bake operator precedence into the whole thing. I also have a GitHub repository. You don't need to take pictures of the slides. I'll share with you later. Right. Then again, after we have the comparison, okay, then we have a term. A term is either something like a factor followed by a plus or minus sign, plus another term, and so forth and so forth and so forth. I hope it gets clear when I show the code in a second. All right. So, right, as I said, one thing you have to be careful is, like, actually, I don't think there's even an algorithm to detect that. But it's like some grammars in general can be ambiguous. So you can like have problems with how they are interpreted, and you want to try to avoid that. So that, let's say, your program language is not just your implementation detail, because different parsers resolve these ambiguities maybe in a different way. Then another thing I did in this design of the grammar rules is I designed it with look ahead in mind. So actually, all of the things, whether you go from one rule or to the next, you can decide by looking at exactly the next token, like an assignment. Right, actually that should be a variable declaration, not an assignment. Look at it. Statements either variable declaration or an assignment or an if statements. Sorry about that. But you look at essentially you look at the next next token, and then that you can already decide which path to go down with. All right. Then also you want to avoid like these infinite loops. I mean, this is just a normal thing. You're going to see it. If you ever implement it, that's some easy bug to figure out. And yeah, like I mentioned, the operator precedence thing. All right. So let's walk through the code and hopefully make everything super clear. Okay. This is big enough, right? Okay. Yeah, so here to the left first, I want to show you a little bit the structure. Actually, it's very simple. We have just, well, here these modules. Each module is defining one phase of the interpreter. So you have the lexer, and this is, again, like I said, it's the only crate I use. I use this logos crate, which essentially allows me to just derive this this trait, and then I can define like these rules a little bit like this, which is just much easier. Here I essentially say, let token is essentially just, well, a token, like one, like a keyword. If is like an if, and so forth and so forth and so forth. I can define it also with regexes. So number literal is this. String literal is, well, it's a regex also. You can't even escape quotes, so it's not a production use language. An identifier, well, a naked regex. Logos kind of does this whole deciding which one to use based on like some rules. Like it prefers longer matching to shorter matching. It prefers specific let, for instance, like specific tokens to generic regexes and so forth. But in the end, well, what it generates is exactly what you expect. So here I have an example source code, let bloop equals 1 plus blah, 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 and so forth. And then it turns that into, well, I mean, I get an iterator back, which I then map to unwrap the tokens, collect it to a vector, and then the result is this. So I have just a list of tokens, and these I can use. Token, yeah, exactly, it's this enum. So yeah. All right. Let's go to the abstract syntax tree. So this is the definition of my syntax. Actually, maybe the order is not great, but let's start with, for instance, the definition of a statement. Well, the expression is also not so bad. So here we have an expression. An expression is either the variable itself, so just using the variable and the expression. can be a function call, can be a factor, a term, and so forth, like all the rules essentially that we defined earlier. Here the factor, for instance, what is it? You have the left, then you have the factor kind, so either multiplication or division, and then you have the right, which is also an expression. So this is kind of how we define the tree. So literally what I showed you in the slides. How do we get from the list of tokens to a tree? Well, here again I pasted the thing. Here I defined some macros to make like a few things a little bit easier. Well, so this parse, what it does is, okay, so my language, the way I defined it, can be evaluated with just one lookup ahead. So I only need to look up one thing ahead, and then I can determine what's language. So I just take a peekable of an implementation over an iterator whose item is a token. So really, with this one peek is enough. The result, the way I defined it, well, statement is not a good example. Let's check, for instance, the block is, I have a result. Well, I was lazy, so I used a string as an error type. And then each one of the definitions that I do, which follow precisely these grammar rules that I designed, basically returns an option of something. What does that mean? Like, when is it an error? When is it a non? An OK non. It's OK, let's say, if the first token doesn't match what I would expect. So a block, like for instance in an if statement, should be a curly brace. That's the only thing that I expect. If it isn't, then maybe we didn't want to parse a block. Maybe we wanted to parse something else, or maybe we wanted to try different alternatives. So I return OK, but we didn't parse it. Once we committed to this, I will start consuming things from the iterator. And then if something doesn't work out, then it has to be an error. I mean, here in the case of statements, well, statements itself is only an error. But let's see, for instance, well, yeah, here in the if statement itself, the first thing should be an if token. And then if it is, we consume that if token. And then we try to parse a condition, which is an expression, right? The first thing that comes after the if, just like in Rust, you can do any kind of expression, multiplication with a comparison, whatever. If it isn't, like we say, hey, there should have been an expression after this if, and then it's an error, because we already consumed from this iterator. There's no way we can go back, let's say. So something didn't go as expected. And like I said, because we designed the language this way, that we know after the first token that which way we essentially have to go, which path we have to go down, then exactly, if there is no expression, we know, like, well, after an if keyword, there's nothing else that can come after an expression. Okay, so it goes all the way down here. Actually, I mean, this is pretty repetitive. Like here, variable declaration, for instance, well, again, the let keyword, if it's a let keyword, here design it the other way around, doesn't matter. But we expect that there would be a variable coming, well, or some identifier. If it isn't, then we say it's illegal token, blah, 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 and so forth. So it's hard for me to know exactly if you kind of understand, but is this more or less clear, or should I go more into detail? I see a little bit of nodding. For anybody who is not clear at all, afterwards come to the talk to me and I show you the code in detail. All right, so here we go with the parser. So last but not least, and this is actually the easiest part, which is this execution, which is this tree walk. This is where things get easy. So we have run this parser and we have turned something into a, well, into this abstract syntax tree. So here I define this execution context, which, I mean, it's just fancy speak, but I have the scopes, so I kind of use the scopes as a stack. Like if I, for instance, enter an if statement, I want to have a new variable scope, right? So if I define a new variable, like a let x equals 10, then it's only valid inside this if block. So it's a vector of a hash map from string to value. And value is essentially just the values that are expressed in this language, which is, I mean, as you see, not production ready. Have no floating point operations. Oh, sorry. Control minus there. All right. And we have this callback container, which is essentially just a fancy hash map storing functions. So this is something like if I want to, for instance, I wanted to implement a print statement and I wanted to make it available into our beautiful language. Yeah, so this is the thing. Let me actually show you an example before we go deeper into how this execution works of like some amazing code. We also don't have else working. Yeah, so this is like the example. I can actually run it. Let me show you. Go. Whoop. Test if. All right. So actually 22 is equal to 22. Who would have thought? All right. How does it work? Well, like I said, it's not rocket science. We just walk the tree. So here, as a start, we get a list of statements, or well, a slice of statements actually. And then over each of the statements, we execute that statement. And then it just becomes a thing of matching the Rust enums. So here we have if it's an expression, we just execute that expression. It could be, for instance, a function call with a print. If it is an assignment, we execute that assignment. If it's a variable declaration, we execute a variable declaration. How does a variable declaration look like? Well, we just take the scope, which is the last scope that we have, check if that scope contains the key, and if it does, then we say that was an error, that variable is already defined. Otherwise, we insert it. Okay. Let me show you. Maybe the next interesting one would be how do we execute an expression here, right? Here, like an expression, either it's a string literal, so we return a value string, and so forth. And then for a factor, for instance, we just, well, do the thing. We evaluate the left part of the factor, we evaluate the right part of the factor. If it isn't numeric, then that was an invalid operand. Then we get the values, we perform whatever we want to do, for instance, a multiplication, and then we return that value. So kind of as you can imagine, we really just descend down the tree, execute all the stuff. At each node, we return what was the result of that execution, and then return that to the top until we get the values that we want. All right, so this was kind of the super abstract thing. Let's make it even more practical. And I'm a little bit nervous about this part, but I'm going to do some live coding, like I mentioned, of implementing a while statement. So let's do this. I won't be holding the microphone, so I'll try to speak very loudly. Whoa. Okay, or I get my friend Roberto here. Amazing. All right, so let's get started. We have to start in the in the lexer because we want to first have the while as a keyword, right? So let's copy paste. That's how the pros do it. And of course, it complains while, and here we have a while. All right. Okay, first part of the exercise done. Next, let's modify the abstract syntax tree because this is actually where the fun begins. We want our statement to also extend that to a different kind of statement, which is the while statement, which contains information about the while. While statement, I mean, from the semantics afterwards, it's very different, but actually, it's essentially the same information that we need as from the if statement, because, right, we have a condition, and then we have a block that we want to execute, right? Actually, yeah, here, let's keep the naming consistent. Okay, So next part, done. Here the tree walk will now complain because of beautiful Rust pattern matching, because we don't handle that case. So let's add a to-do here. Okay. So next part, well, we do it later. Okay, and now we go to the actual difficult part, which is the parsing. So here I have this macro defined, which, I mean, it's not magic, actually, just I was too lazy to write like match whatever we're trying to do. If it's an okay sum result, then return this the result. If it's an error, return an error, else don't do anything. So here. But so let's add another one. Here, whoop, the while statement, and then we have to define that function, token stream. Okay. So I could copy paste this, and it would be pretty easy, but let's try to do it from scratch because, I mean, I have to do some work. While statement. Okay, this, I have no shame copy pasting the definition here. Okay. All right, so what do we need to do? We need to, again, verify, like, is this a while statement or is it not a while statement? Like, do we want to parse this? I do this like this. I check if, okay, if token stream dot peak is a token while. Actually, let's do it the other way around. If it's not, whoop, then we will return okay none. Yep, there we go. Let me put a to-do here so I don't see so many errors. Why do you complain? Yes. Probably I could do something better with matching, but here we are. Okay, otherwise, okay, so next thing we have to do is, I mean, we don't want to like confuse the expression that we're going to get. So we will just then go and advance. Like as soon as we know this is a while, we next. So skip while token. All right, and then we say what's the expression block, like the condition. So let condition equals, and here we just simply parse an expression. It's that easy. So we parse an expression because we have everything very well defined. We get, like, if there's an error with this parsing, we return that error. And then we go OK or, because if there's no expression, then we know, like, we want it after the while, we want some expression. Right? So I say expected an expression. Let's be super user-friendly and add even something nice here. But got token, yep, and then the token stream dot, and here actually, that's where my expect peak comes into place, because this expect peak, what it does is it tries to peak, and if it's none, like if we're at the end of the thing, it returns an error. Like essentially I'm doing here some extra work. Okay, so this semicolon. Good. So we have our condition done. Oh, we should probably also return the error in the end. So here we have already our expression. And then we want to just parse the block. And let block equals, and then we just parse the block, right? So I have already the function defined here, token stream, which parses a list of statements. If this doesn't work, well, we return the error. We say OK or expected statements. Some statements are expected a block. Statements, whatever. Yep. Okay, question mark, semicolon. All right. I may have misspelled that one. Okay. So far, so good. Are we all cool here? Yeah? Amazing. Okay, and then we just return that. That while statement, just to like escape a little bit this formatting hell. We do like the while statement. Right, there they are already. And then return, okay, it's a statement, app statement, while, and then the while statement. And then that's it. That was the parsing part. No errors, all good. Should we write a test to see if this works? I would rather. Okay, I mean, there are a lot of tests, but what is this? Yeah, okay, way too complicated. Let's write a simple test. Test fn test simple while, and then we I have here some helpers defined for my testing. So yeah. Yep. Lex test source, exactly. And we say while, and then we do this. And then what we want is, okay, here's again the famous copy pasting that I do shamelessly. Cert. Here I'll just copy this part because it's literally the same, except with a while. While. Okay, AB, okay, this is fine. This one I deleted, but actually, why don't I just add it back so it's, there we go. Okay. Good. So, will this pass or not? Anybody paid attention? Let's see. Okay, first try. Actually, I lied. I practiced yesterday. All right. Last but not least, the tree walking. So this is the part where we actually have to do some work. Again, we do self.execute score while underscore statement, while statement, and a question mark here. Can I? There. Let's do this. Haha. And here we want to return a result of nothing, probably, because, yeah, result either nothing or a execution error. Okay. So what does a while statement execution need? Essentially, we will first, okay, so we need a loop, right? This loop will run while we match certain things. What do we match? We match self.execute expression because we want to check the comparison of this or the condition of the loop, right? So while statement dot condition. Okay, so and a question mark here, because if we cannot execute this expression, then we have an error, right? If we cannot execute like, yeah, I mean essentially that. Let's fill those arms. Yes. This is the part where it gets fun. So, for instance, if our, I mean, it's a generic expression, right? This could just be a string literal, and we would parse that, and it would work. But, I mean, in that case, we want to say, hey, we cannot do a while statement with things. So actually, let's just handle the first two acceptable cases, which is if this is true, we execute the block, which is like this self.execute block. I have all the functions already defined, which is the while statement dot block, right? I mean, it's just a list of statements. And it does that by adding also something to the, like a, another element to the scope, to the stack of scopes. All right, so we want to do this. If it is a value Boolean false, everything is good, but we want to leave this loop. Break. Okay, now I'm curious, why is this complaining? Ah, right, yeah, missing match arms. Hey, sorry, I thought it was going to fill the match arms. Yeah, there we go. Actually, no, you know what? All the other cases are all an error. So we just want to return an error. Oops, sorry. Up, error, right. Return R, and then execution error, and then what do I have here? Invalid operand. Let's go for that one. Okay. Here we have some complaints. Ah, right. It has to be mutable self. Because, well, we have to either mutate the scopes in certain conditions or so forth. So, okay. So I think with this we are good. Famous last words, I know. Right, we don't need to do an OK loop. I can just put that here. OK here. And there. All right. OK, so let's run create a test for this. Tests are here also very simple with the helpers. So I have test simple underscore loop. Okay, so we test, all right, I don't have smaller than comparison either working here. So we just have to, just gotta do it like this. While x is not equal to 5, let's define another variable, that y equals 1. We do y equals y times 2. All right. And then we should, in theory, get 2 to the power of 5, if I'm not mistaken. Right? Up, right, yeah. Infinite loop. I know how to write Rust, but my toy language is still +1. Good catch. So you are paying attention, that's good. Okay, anybody see any mistake with this? Except for, of course, x 2 dots pow 5. What am I missing? All right, underscore I64, because we have, well, 64 bits. Okay, let's run this. How much confidence do you have? Okay. Okay. I'm sure there's a reasonable explanation for this. Right. I mean, we just missed 1 power, actually, because we executed from 1. So 1, 2, 3, 4, and after the 4th time, it's already. Let's just pretend that this is what should come out. I think actually this is right? You started from 1. Right? Exactly, I started from 1. So I think the test is right. It was just my assumptions that were wrong. And are we good? We are good? Okay, amazing. So all right, so Turing complete. Can calculate primes. I think let's get some funding from Google, and in 2 years we're good to go. Yeah, so this was it. This was also it for my talk, I think. I only have like some resources I want to share with you. Exactly. Here's some references. Actually, there's this there's this book, which is, I think, the cool. Like it's really exhaustive, a bit theoretical maybe. It's a practical approach to compiler construction. Published in 2017, I think. And then there's an online resource, which is really nice. The only downside is, and I didn't want to shit on other programming languages, but I mean, we're at a Rust talk, so we have to. It shows you how to write an interpreter in Java. But yeah, so this is it for my talk. Thanks. Any questions? Ooh.
What name will you give to your language, to your new language?
I mean, the GitHub repository is, I think, called Toy Language.
Okay.
But yeah, I'm open for suggestions. Any other questions? Yes?
I think someone said that like AI is not very good at writing Rust, or I don't write Rust, but do you use AI to write Rust? Or?
I don't to write the production code, but so what I sometimes do is, or what I did as well in this case, is I write a test, write it how I like it to be, and then there's like 5 more cases like this test. So I just say Copilot, hey, implement the rest of the tests.
I'm just curious, like, well, we can't really test it right now, but if you told an AI agent to add, for example, support for a while loop, how well it would do in your code base?
I mean, it's actually a good question. I mean, I have Claude Code installed, and we can check it out later. May not work super bad because we have a lot of surrounding code where you have all the examples already done. But for writing completely new code, like a lot of things, I don't know. I mean, you were the one who mentioned it, that it doesn't work well with Copilot. I mean, for me, it's usually lifetimes that don't work well, or just, generally. I've seen, like, I tried it a few times. It worked well for me with Python with some simple scripting, but for Rust, it, didn't generate good code. Yeah.
On a high level, I think it's actually very similar to the cell parser of Rust.
Oh, yes. You are making a good point. I actually wanted to show you some, or I can, if you want to, show you some production Rust parser code, and it looks pretty much the same way that I wrote. So, I mean, I can just open it. Is that a question or just no? Okay. Let me sit down. Yeah, with the lights. Okay. Yeah. Actually, I was thinking of including it, but I didn't want to make my talk longer than an hour. So you're getting actually the bonus part. So let's open Rust. Look, we have the parser here already. So here we have the parse, like it's all organized into crates. Here you have, for instance, the abstract syntax tree definition. And there, for instance, well, I mean, here, it's literally the same thing, right? You have like, I mean, they have a few more lines of definitions, but essentially, yeah. You see, I mean, here you have like the whole abstract syntax tree. Then for the compiler, for the parser itself, actually, okay, we need to have the compiler, but we want the parser. We don't want the abstract syntax tree. Up. Let me not scroll. Rusty passes. Sorry, like with this small screen, it's a little bit difficult to find it. Okay, here you have the lexer, for instance. Also, like, interesting, right? You have like the well, they didn't use the logos crate, but I mean, all the essential, right, here we are. All the essential steps are exactly the same. Then you have like some parts of they have more intermediate steps. So this mid-level representation, high-level representation, and so forth. Right. Let me see if I find a good, for instance, this one. They have this one trait, and then they have implementation, like the different implementations, they split that into the different mods. But here, for instance, you parse an expression. Well, actually, I mean, I didn't write this whole thing. It would be difficult for me to go through the whole thing. But like, you do this recursive descent. So you'd start with like something that you expect, then you go deeper into the thing. They didn't go that route with the option thing. They did it the other way around. So they check, is it this type of token, then start parsing it. Whereas I go, try parsing that. If it is this type of thing, return me an OK sum. And if it isn't, just an OK none. But yeah, I mean, you recursively descend into the code through these tokens. So good comment, good point. Any other questions right now? From my friends at the back. No?
So are you going to add a garbage collector, or is it going to be
I mean, I think the entire language is garbage, so. What I actually was thinking of, like a next toy project, is to write a code generator for the JVM, because you already have like a virtual machine that works really nice, and you just have to produce the bytecode. And that's something really nice, honestly. I think would be a cool next personal project, future Rust talk maybe. Yeah. Okay, then I think that was it. Thank you very much.